Hello everyone, this is the fourth lecture of this week. In the last class we discussed the formulation of analysis for 3D truss. Today we will translate that formulation into a code and demonstrate that code through two examples. The first example we will consider is this one, which is relatively simpler in terms of number of members and number of nodes, and the second one is this example which has more number of nodes and members. So, let us start with first this one. So, it has so first thing when we have a problem, the first thing we have to do is we have to give the numbering of the nodes. Suppose this is node number 1, this is node number 1, this is node number 2, this is node number 3 and this is node number 4. Okay. And say, and the members are, this is member number 1, member number 2 and member number 3. Okay. So, member 1 is connected between node 1 and 4, member 2 is between 2 and 4, member 3 is between 3 and 4. Now, all these joints, joint 1, joint 2 and joint 3, they are hinge joints. So, essentially displacement at these joints are 0. Now, the degrees of freedom, since it is a space truss, at every point we have 3 degrees of freedom, and suppose these three degrees of freedoms are, this is your 1 and this is 2 and this is 3. So, this is U1, this is U2, this is U3. Similarly, we have here this is 4, this is 5 and this is 6 and this is 7, this is 8 and this is 9, and similarly we have this is 10 and this is 11 and then this one is 12. Okay. So, it has total 12 degrees of freedom. Out of these total 12 degrees of freedom 1 to 9, they all are hinge joints. So, they are all constrained. So, U known is equal to U1, U2 to U9 and this is equal to 0. Displacement at these degrees of freedom are 0, and U unknown for which we have to solve this, that is only U11, U12 and U10, U11 and U12. Okay. Now, nodal load vector, suppose we have a load of here we have a load, concentrated load of 10 kilonewton. Okay. So, P which is in the direction of 11 degrees of freedom, then P11 will be minus 10. Okay. And all other P's will be 0 as for node number 4. So, now let us give this information to the code and then see what is the result, and in the process we will also discuss the various steps in the code. So, to start with, this is the code. Now, these are the nodal coordinates of different nodes, 3 nodes, and this is the member connectivity, all these members. Now, total degrees of freedom for this is 3 into n, 3 degrees of freedom per node. So, total 3n degrees of freedom. This is member property. Now, you can have different, these look at, please note that E and I, they are essentially vector. So, for demonstration purpose, let us assume they are 1, but you can have different values depending on the member property, and we have to change the corresponding element in that vector. Okay. So, this is the initialization of the displacement vector and the stiffness matrix. The stiffness matrix, size of the stiffness matrix will be 3n by 3n. Now, this is the applied load. This is initially we substitute all the values as 0, and then only the force we have here is only in the 11th degrees of freedom we have minus 10. So, this will be minus 10. So, P11 will be minus 10. Okay. Now, just now as I said, the all known displacements are 1 to 9, they all are constrained. So, essentially those values are 0, only unknown displacements are 10, 11 and 12. We have to solve for this, and K11, K22 are the same. This is the partition stiffness matrix. If you recall, we discussed that in the case of 2D truss as well. The total stiffness is now partitioned into K11, K12, K21 and K22, right. Now, so this is K11 and this is K21, K11 and K21. Okay. Now, this is the computation of stiffness matrix. It starts from here. So, this loop is over the number of element. First determine the length of a given member once we know the coordinate. These are the Cx, Cy, Cy or the lambda x, lambda y, lambda x, lambda y and lambda z, if you recall. This is how it is related to, this is lambda x, this is lambda y and this is lambda z. Now, once we have lambda x, lambda y, lambda z, next thing is the transformation matrix. The transformation was, again if you recall, the transformation was T was lambda x, lambda y, lambda z, then 0 0 0, then 0 0 0, lambda x, lambda y and lambda z, right. This is the transformation matrix and this is that matrix, this is this matrix, right. This one is this transformation matrix. This is the transformation matrix and this small k is the local coordinate system. If you recall, local coordinate system or local coordinate system is 1 minus 1 minus 1 1, then AE by L, that is the stiffness matrix of a member, and this is the stiffness matrix with respect to local coordinate system. AE by L is not multiplied here, it is multiplied at the end here. Now, if you recall, then the global stiffness matrix, global stiffness matrix was, means stiffness matrix with respect to global coordinate, that was AE by L, AE by L and then T transpose K into T, right. This is the expression for stiffness matrix and this operation is performed here. So, this is the stiffness matrix or member stiffness matrix with respect to global coordinate system. Okay. Now, once we have member stiffness matrix, then we have to along with the member stiffness matrix, we know the connectivity of the member and also know the therefore, we know and we also know the definition of different degrees of freedom. So, we know that a particular elements in the stiffness matrix, member stiffness matrix corresponding to which degrees of freedom, right. So, then based on that we have to populate the global stiffness matrix. We initialize the global stiffness matrix at 0 and then element wise, for every element we take for every member we construct the stiffness matrix and in that stiffness matrix we compare element by element and then put that in the subsequent places in the stiffness matrix, global stiffness matrix, and this is done here. Member stiffness matrix is 6 by 6 here, if you recall. So, this is the assembling of the stiffness matrix. The resultant, the Kg, will be the global stiffness matrix. Okay. Now, once we have the global stiffness matrix, next is we have to partition the stiffness matrix. Partitioning of the stiffness matrix is done here. K11 is this and K21 is this, and then this is the load vector. Correspondingly, we have to partition the load vector as well. So, this is the corresponding load vector, and then what we have is we have P, if you recall, then we have K11, K12, K21, K22, all K11, K22, they all are matrices. Then this is equal to U unknown and U known, that is equal to P known and P unknown, right. So, from this we'll have this expression K11 into U unknown unknown is equal to P known, because U known is 0, that is why this contribution will be 0. So, if we solve this equation we get U unknown. So, this is done in this expression, it is solved for U and then this U give you the solution of this unknown displacement. So, once we have the unknown displacement, next step is we have to find out the support reaction, and what will be the support reaction? Support reaction will be, we have to consider the other part for the support reaction, for this part for the support reactions. So, P support reaction will be, if you recall, then K21 into U is equal to Pu, this gives you the support reaction, right, and this support reaction, this is been done here. So, once we have the support reactions and then the member forces, this is the member force this is the member force is calculated here. If you recall, the member force, the expression for member force for 3D truss was it was minus, just 1 minute, let me come to that. Yes. So, it was, if you recall, the member force for a given member, the member force is F is equal to AE by L, AE by L, and then we have lambda x, lambda y, lambda z, then minus lambda x, minus lambda y, minus lambda z, and then for that particular member, for that particular element, what is the V. Okay. So, if you from that we get the we get the member forces, and this is exactly performed here. So, this is this. Okay. Now, once we have the member stiffness, member this, then we have all the information which is required for the analysis: support reactions, displacement, and the member forces. Now, let us run it and then see what are the result. Coordinates and everything are given here. So, run it. So, this is the plot. This is not a 3D plot. Actually, the structure is in 3D. This is a 2D projection of the plot. So, that is not important right now for us. So, let us see what are the values of displacement. First, you see what is the displacement total u. You see all the first 9 u will be 0 because they are constrained. Then we have rest of the u 10, 11 and 12. These are the values of u 10, 11 and 12. And then the support reactions, if you take the support reaction, these are the support reaction. The first 3 is for joint number 1. This is for joint number 1, this is for joint number 2, and this is for joint number 3 in the corresponding direction. And similarly, we can calculate the member forces. Member forces will be this. So, this is 3 members, these are the member forces. This is for member number 1, member number 1, member number 2 and member number 3, right. Now, you can these truss, since it is smaller comparatively, you can do it manually. You do it manually and compare your results with these results, and then do other exercise like you change the Young's modulus, change the area of particular member, and then do this exercise to get some idea about the structural behavior. Because you see, if you in a truss, if some members are having say smaller dimensions, or some members are having smaller lower Young's modulus, then what happens to the behavior of the structure? So, that exercise if you do, you get that comprehension may come. So, this was for the first example. Let us do it the similar exercise for the second example. So, second example was this. This is the second example, and suppose, and this is, if I draw the line diagram will be this. Okay. Now, in this second example, let us first give the numbering of this node numbering. This is node number 1, this is node number 2, this is node number 3, this is 4, this is 5, then this is 6, 7, 8 and 9, and similarly we have 10, 11, 12, 13 and 14, and then this one is 15, then 16, 17 and 18, total 18 nodes. These all are nodes. Okay. Now, the coordinates of these nodes are written. I will show you the coordinate, and suppose it is subjected to some load. At all the places we have some load. Okay. And these are all loads. Okay. Now, for member number 1, the degrees of corresponding degrees of freedom will be this is 1, this is 2 and this is 3. Member number 2, similarly it is 3, 4, 5, 6 and so on. Now, so what another information from here is since from node number 1 to 5 and 10 to 14 they are hinge joints, so corresponding degrees of freedom will be 0. So, U known will be, it is your degrees of freedom 1, 2 all the degrees of freedom associated with these nodes. Okay. Let us not write it here. So, see the code. Now, this is the code. This is we have the another one. This is the code. Okay. This is the nodal coordinates given and corresponding connectivity of these nodes are given. Okay. Connectivity of the elements are given. This should be 3. 3 into number of nodes, the degrees of freedom, that we discussed. Now, this is, you see, this is the load on the top on these nodes, on these nodes. These are the loads. So, if we this is corresponding to it is degrees of freedom along the y axis. So, we have to those values will be only non-zero and rest of the values will be 0. So, this is the nodal vector. Now, the boundary condition, this is known degrees of freedom, again this is unknown degrees of freedom, we have discussed this, and finally, the same procedure, it is also the same procedure, and then finally, we have the K1 and K2. So, only thing, the rest of these, all the steps are general, only thing that we have to give input is the information about the configuration of the structure, information about the boundary, and information about the load. Now, you see the purpose of this code, for instance, if you use any software, that software really, you draw this and you apply the load using graphical interface, which is more which is where you don't have to really give all this information in writing. You can do that through a graphical interface. But here the purpose is to demonstrate the fact that this how easy the method is to translate to getting translated into a computational code. Now, so if I solve it, then if I solve it this, so this is again this is a projected 2D deformed shape. Now, if I see the say total displacement will be this, these are all total displacement. These zeros that you can see, that is corresponding to the degrees of freedom which are constrained. And then the support reaction is Pu. The support reactions are this. If you join all the support reactions, then what will happen is you should be getting the total load will be 0 if we join them. Okay, whatever load we apply on the structure in the corresponding direction, if we join them, that equilibrium should be satisfied. It is a very important thing. You see, all these when we derive this in the formulation equilibrium equation we use. So, naturally they satisfy equilibrium equation, but the problem comes when you translate those equations into a code. So, it is very important you validate your code, just not the final results, you validate every steps in your code. For instance, whether one check I can make is check whether the whatever forces I am getting, whether they satisfy the equilibrium or not, right. So, these should be we should check that. Then Kg, if you check the total stiffness matrix, the global stiffness matrix is huge, it is a global. Now, you see the maximum entity, it is a very important, we will discuss that towards the end, is the maximum entity in the global stiffness matrix is 0. Okay, some of the values are non-zero. Now, so when you actually store a stiffness matrix, in this case the stiffness matrix is say here number of degrees of freedom is and number of here number of degrees of freedom is how much, let us see, it is yes. So, it is number of degrees of freedom is 54. But you know, you can have a structure where number of degrees of freedom huge in terms of 1000. So, and in that case your the size of the stiffness matrix will be 1000 by 1000. If you see real structure, it is not even 1000, it is much more than that, your size of the stiffness matrix. But if you look at the stiffness matrix, the most of the entities in the stiffness matrix is 0. Some of the entities in the stiffness matrix, depending on the connectivity of the member, some of the elements in the stiffness matrix will be non-zero. So, in that case, the storing of stiffness matrix, storing of that stiffness information is an important part in the code. One way is, very crude way is, you store stiffness as a matrix in a matrix form. But when you store in a matrix form, if the size of the matrix is say 1000 and 1000 by 1000, so essentially you are storing 10 to the 4 elements, 10 to the 4 information, even it is 0, but you are storing it, right, when you store entire information in a matrix form. But since most of the elements in the stiffness matrix is 0, you can store in a different way. You can store only the non-zero elements in the stiffness matrix and their corresponding position in the global stiffness matrix. So this is another aspect when you write a code. So you have to see how these matrices, all these always better to avoid these matrix operations, inversion, storing, if we can do it in some other way, that you have to find out. Another important thing is, we mentioned some time back during the discussion in some of the discussion earlier, that you can change the numbering pattern. See, whatever way you number, if your degrees of freedom, numbering of the degrees of freedom and the numbering of nodes are consistent, you will get the results. There is absolutely no problem in that. But if you change the numbering pattern, then what will happen? You make your stiffness matrix banded. Banded stiffness matrix means the diagonal term and some off diagonal terms will be non-zero. Immediate off diagonal terms will be non-zero, but rest of the thing will be 0. For instance, one example of banded stiffness matrix is, if I have to write some example, suppose it is 1, 2, 3, 4, and then so you have a stiffness matrix, and then this is a diagonal entity, and then you have some off diagonal entity here, and then some off diagonal entity here, another off diagonal entity, another off diagonal entity, and this is 0 and this is 0. All the elements here is both triangles, upper and lower triangle will be 0. So this is banded stiffness matrix. You can achieve this banded stiffness matrix by changing the numbering pattern. If you number it haphazardly, what you can have is you get a matrix, but those matrix is populated in such a way that this feature you won't get. You get something like this. For instance, this matrix, the numbering is done in a very arbitrary way. This may not be a banded stiffness matrix, you see. So here it is 0, then non-zero, then some of the elements 0 here, and then some of the elements 0 here. So so that we'll discuss later, what would be the numbering pattern, so that you can get the stiffness matrix in this form. So this is important that you keep in mind when you actually number the nodes. It is just not numbering haphazardly. We check the determinant of kg, just a cross check, determinant of kg is 0, it has to be because the boundary conditions were not satisfied. So this is now you can explore, as I said, these codes will be uploaded on the forum. This is a very basic code. Some of the information actually you have to do it, you have to give manually. But it gives you a flavor that of computer implementation of the method. So you can further explore it. You can solve some other different problems using the code and check with other software and your solution, and also you can do some exercise like changing the Young's modulus, make one suppose you have a truss where you have 100 members and make one member very soft in the sense you reduce the Young's modulus of the one member drastically, and rest of the members Young's modulus are same, and then check what is the behavior of the truss. Are you getting any localized behavior on the knot, or are you getting a localized deformation at a place where your elements, your members are weaker. So these are the important things. Through this exercise you can have some, you can develop some comprehension, some idea about the behavior of the structures. Okay, so here I stop today. So next class what we do is we do the similar exercise for beam. Again we will take 2 problems in beam and then see how using this code those beam problem can be solved. Okay, see you next class. Thank you.